Yes, I'm ready.
So, hello everyone, my name is Lydia and I have a great pleasure to open the third session of seminars organized by NGSchool Society. Today's workshop is an introductory course of R and it will be conducted by Maja Kuzman. Maja works as a research and teaching assistant at the University of Zagreb. And she is a PhD student with an academic background in mathematics and master degree in molecular biology. She works in the bioinformatics research group, and she was also a co-organizer of previous editions of NGSchool. So you are in good hands. Let's learn hard and have fun. Hello, Maja.
Thank you, Lydia. Okay, so I didn't prepare anything for you to install before this seminar because I teach usually R as an introductory course, and I expect you to know nothing. And by expecting you to know nothing, we will start from the beginning. So if you don't have R installed and you don't have R Studio installed, this is fine because we will do it on the cloud now together. So please just go to the web browser that you use and write this address. So bit.ly/NGSeminar. When you write this, it will take you to this repository. So this repository on NGSchool contains all the material for today's lecture, as well as the information about where you can use RStudio online. So I really recommend you to use RStudio on the cloud. Although it is a beta version, it seemed to work fine for now, so I hope it's going to work fine today as well. So if you haven't installed it, if you haven't signed up before for it, you can sign up now, and it takes around like a minute or two. So you can use, it's the easiest to use your Google account or anything like this as you wish. But since I've done it already, I'm just going to log in. After you log in, you will be at basically at this cloud, and in this cloud you can run the RStudio. You run RStudio by going to your workspace, and then in this new project you just click add new project from Git repo. So we'll just copy the repository that I prepared for you, and it will, so all the materials will be copied in the session that you will use. So the site is the same one that we used. So it's the one which you get when you write this bit.ly NGSeminar. So just copy this repository and then start it as a new project. While this project is deploying, I will also mention something about what I do. So what I plan to do today, I plan to give you a short introduction to R. I plan to give you the short introduction to ggplot, which is the most amazing visualization package ever used in R. And this is, I think, the reason why R is so popular and widely used. And I'm going to introduce you to my favorite package, which all of the people who know me really well know everything about this package. So it's called data table. As you see, this is quite a bit of work to do in 2 hours. So I'm not really going to go into details, but you'll see how it's going to go, and I think it's going to go pretty fine. If at some point you miss something, please ask on the R channel on the Discord, or just we will try to answer as soon as we can. Okay, so as Lydia mentioned, I used to study mathematics, but then I took a bioinformatics course, and I thought to myself, oh my God, I think I can do this better. So I was really interested in programming there, and I really wanted to include more biology and to program better than what I've seen is being done in this introductory course in bioinformatics. So I decided to get enrolled in molecular biology, where I finished both the bachelor and master's And then I enrolled in bioinformatics as a PhD student. And I thought that finally I will be able to program in bioinformatics. But unfortunately, it didn't happen. So what happened is I got introduced to R. And when you go to our webpage, the thing that is written there is that it's a project for statistical computing. And it says that it's a free software environment for statistical computing and graphics, which means, I mean, nowhere here is it stated that R is a programming language. And actually, if you're using it as a programming language, you're probably using it wrong. This was something that took me quite a while to understand, because if you're trying to use R as a programming language, everything will be super slow and you will have no idea why people are using R at all. So today I'm going to teach you how to use R as a data scientist and not as a programmer. Okay, so by now this should have happened. So you should all have RStudio opened, and what you see here in front of you is called the console. So you can write in it. You can write, for example, 1 plus 2 and push enter and you will get the number 3. You can also write something else, like more challenging, and you will get the result. What I'm trying to show you is that whatever you write here is executed automatically and is interpreted as R code. So the problem with the console is that this code, of course, is not saved anywhere. It's just run. So if you want to save code, you can write an R script. To write an R script, you go to this little plus button, like create new and R script. Here, when you write 2 plus 6 and push enter, and then you write 6 plus 9 and push enter, absolutely nothing happens. Why is that? Well, that's because this is a script. So you're supposed to write in it, but you're not running any commands. How to run commands? Whenever you push, put a cursor in some line and hold Control and push Enter, this line will be run. You will see that it's run because it will be ran in the console and you will see the result there. If you want to run multiple lines at one time, you just highlight multiple lines and press Control and Enter, and both lines will be executed. Okay, so, sorry. I will zoom in so you see better. Okay, the interesting thing about this is, so whatever is highlighted, it will be executed. If you highlight just the number 9, push Control and Enter, just the number 9 will be executed. This is useful. You will see why. Yeah, the problem with our scripts is that if you write some words, like some words, and try to execute that, you will get an error because everything that you write here is supposed to be an R script or is interpreted as a R command. So if you want to write, I will close this now. If you want to write both text and R code, this is possible in R, and it's this is why we use R Markdown documents. I prepared R Markdown documents, and the first one that we're going to use is this Intro to R. You will notice that I have both the solved version and the not solved version, so please use the not solved version. And if you need a hint, you can look at the solved version, like if you're stuck somewhere. Okay. So you can use R by a console, which you will never do. You can use it with a script. You will only do this if you use it in a pipeline. Or some people prefer scripts. I really don't. Or you can use it as a notebook, which is what we are doing right now. So you can notice here that whatever is written is just a normal text. And if you try to produce a document from this, it will create a lovely HTML document, which we will do in the end of this lecture. Okay, so how to write code? There are special parts which look like this, and they are here so you can write code in them. So now again, if you press Control and Enter, this part is executed and you see the result right below the code chunk. Okay, so there are multiple ways how you can execute something. I said you can highlight it, you can just put a cursor and hold Control and Enter, or you can push this play button. If you push this play button, all the code which is in this chunk will be executed. Okay, now you can try it. So add a new chunk here on line 29. You add a new chunk by holding Control, Alt, and E, or I, like insert. This should happen. And then I ask you to calculate the result of this command, 13%3. Okay, the result of this command is 1. Can you maybe guess what this does? To get you more hints, you can try 12%3 or 15%3 and run everything. So the first line is the result of the first command, the second line is the result of the second command, and the third line is the result of third command. You see that, you might see that percent operator is actually the modulus. So it's when you divide two numbers, the rest from the whole number division. Maybe I can write it like this. So 13 divided by 3 is equal to 4 plus 1 is left. So this rest, when you do this division, is what this operator gives you. Why can this be useful? Because when nothing is left in the whole number division, then you know that two numbers are divisible by each other. Actually, that the first number is divisible by the second number. Okay, so what have we learned so far? Well, we've learned that we can use R as a calculator, but I promise you that you can use R for much better things than this. So to get to the better things, I need to teach you what are variables and what kind of data structures we have in R. So if any of you ever did any kind of programming, you know what variables are. Variables are just containers for your data. So for example, when you use, okay, so let's run this code chunk. When you run this code chunk, nothing happens. You don't see any output. But actually, if you look at the right side, you will see that in your global environment, or in our studio now, in your session, there exist two variables or two containers for data. One variable holds just one number, and the other variable is actually a numeric vector, and it holds 4 values, and these values are 2, 3, 7, and 8. So you see that this assignment operator, it's what it's called, just assigns the value to some variable. It doesn't produce any output, but this value is stored. How do you know that it's stored? You can see it in the environment, or you can use the ls function, which will tell you which variables are currently available in your session. Okay, so to look at the number or to look at the variable content, you can use print, which is similar to what is normally used. So when you print my first number, you will get the number 0.1, and this is what you expect to get. But also there is another way to access the content of this variable, and it's just to call the variable by its name. So if you just write the variable name and highlight it and execute this part, you will see the same solution. So nothing changed because both commands gave us the same solution. Okay. What I've shown you here are examples of vectors. Vector in R is any container that contains elements of the same type. Other than vectors, there are different data structures in R. So if you have some other data that you wish to store differently. For example, some mathematical object, you can store it in a matrix. A matrix is two-dimensional vector, which contains all the elements of the same type. If you want to store some of the elements of different types, you cannot use a matrix, you have to use a data frame. Data frame in R, you can imagine it's just an Excel table. So when you have any kind of table, you can read it into R as a data frame. A list is an object, a data structure in R, which can contain various number of elements, and they can be of various sizes and various types. And lastly, there are factors, which are the source of most problems in R, but I will not go through any of them today, because I think that you'll be able to follow and become amateur data scientist just by using vectors and data frames or data tables. Okay, so we will now start with the basics of vectors. This is the actual beginning, and everything else was just the introduction. What can we do with vectors? Wow. Okay, so first thing you can do, you can make a vector. To make a vector in R, you have to use this function C. It stands for concatenate. So whatever you put inside the normal brackets will become elements of the vector that you're producing. For example, if we run this, you see that my first vector now is a character vector, and it contains 4 elements. Okay? My first sequence is now an integer vector, and it contains also 4 elements, numbers 1, 2, 3, 4. You may notice that I defined a character vector with C, and I defined a sequence or numeric vector with this double dot. So if you want to use, actually, this is the proper way to define any vector in R. This will give you the vector with 4 elements. And if you want to define a sequence, this is just a shortcut. So to define a sequence from one number to another number, you can use this double dot. Okay. Now we know how to define a vector. So just use this concatenate function or C. The next thing we are going to learn is how to subset. Well, we already learned how to access the elements of the vector. You can just print the entire vector, okay, just by calling it by name. And you see here that my first vector indeed contains some words, P, awesome, and last one. And my first sequence contains number 1, 2, 3, 4. If you want to print a third element in the vector, you can access it with square brackets. It's similar to Python, except finally now when you try to access the third element, you access it with the number 3. And this is indeed awesome because so the indexes in R go from 1. When you try to access the first element, you have to call it by using the number 1, and you will get the element which is the first in the vector. Okay. I think you can guess what will you get if you try to access my first sequence of 3, and it's indeed the number 3. Okay. What we learned how to create a vector and how to access one element in the vector. If you want to access multiple elements in the vector, you have to, okay, you can use their positions. For example, if you want to access the first and the third element, you might try to do this. So my first vector of, like square brackets, 1, 3. This will not work, and this will give you an error. Why is that? It's because R interprets this as if you're trying to subset over a matrix, as if you're trying to subset into two different dimensions. Like the first thing is the first dimension, and the second number is the second dimension. So what you need to understand from this is that if you want to access multiple elements in a vector, you need to provide a vector of positions to look at. For example, so if my first vector looks like this, and you want to access the first and the third element, this will create a vector that holds the positions 1 and 3. You can check it by highlighting it and pressing enter, and it holds, so it's a vector and it holds positions 1 and 3. And if you run this whole part, it will give you some words and awesome. So it will give you the first and the third element of this vector. Okay, so I'm going to repeat this one more time because it's really important, and it's something that's usually for people who are new to R, something that's causing troubles. So if you want to access multiple elements in a vector, you need to provide a vector of positions you want to look at. So you can do it either directly by not naming the vector, by just providing the vector, or you can create a new vector. For example, let's create a vector that's called some positions. And this vector, some positions, now holds the positions, or holds two numbers, number 1 and number 3. Okay? You can use this vector to subset your first vector, because it's absolutely the same as doing this. Okay? So both things will give you the same answer because you're providing a vector of positions you want to take out from your vector. Cool. Now we've gone so far that I think it's time to answer the first exercise. Okay, the first exercise is create a vector which is named myVector and contains numbers 15, 16, 17, 18, and 20. How to start? You need to insert a new code chunk. You will insert a new code chunk by pressing Ctrl, Alt, and I. Insert. Okay? When you've done this, way to create a vector is to use this function C. I said whatever you put inside the brackets will be concatenated together in one vector. So we want to put 15, 16, 17, 18, and 20. And the way to assign this to a vector is to use this assignment operator. It looks like a little arrow, so smaller than and minus. And assign it to some vector that you will call myVector. Okay. Now myVector contains these numbers. Okay. There is a power user hack called tab completion, which you might have heard of in Linux course or whatever. If you are listening to any kind of seminar, for example, in NGSeminar courses before. So basically what I'm trying to say is this. If you start typing variable name, for example, myv, and you push tab, it will autocomplete until the end of the object. So you don't have to type in the entire word. You can just type the beginning and push tab, and it will autocomplete. Okay. Now, the other way you could have done this is this. myVector is equal to this same thing. So it's absolutely the same as using this assignment operator. It will do the same thing. Just for some reason in R, it's common to use this assignment operator arrow instead of equal, but some people use equal. Whatever you use, just be consistent. I will use this, and I will try to be consistent in it. Okay. How will we get the second and the fourth number in this vector? Well, there are different ways. So you can either provide the vector, which holds the numbers 2 and 4, or you can define a new vector and then subset by this new vector. New vector that holds these numbers, and then subset my vector by this new vector. Okay. Another thing you could have done here is to do this. So instead of writing all the numbers, since 15, 16, 17, 18 are numbers in a sequence, you could have used this. So this would have given you the same result, because you just concatenate together the sequence from 15 to 18 and the number 20. Okay. So I hope that everybody is clear now on subsetting by positions. If you're not, please ask so I can repeat something. But if you are, we have another very important question to go through, and this is accessing multiple elements by inclusion. What does this mean? It means that we will provide a logical vector to say which elements we will include. I can explain it better if you see an example. For example, your first vector looks like this, and if you want the first and the third element, you can provide a logical vector. This logical vector holds 4 elements. First one is true, second one is false, third one is true, and the fourth one is false. Wherever you put true, elements which are on these positions will be returned, and wherever you put false, elements in these positions will be ignored. What does this mean? It means that if you subset by a logical vector, you will only get those positions in the vector, those elements which are on positions which are true. So in this case, you will get the first and the third element, which is some words and awesome. Okay. Same as before, you have to provide a vector of a logical vector by which it can subset. So you can either use this way of creating a vector within what you're trying to subset, or you can create a logical vector. So let's create a logical vector that has the elements true, true, false, false. Okay? Now this vector can be used to subset my first vector, and probably you can guess what we'll get. We'll get the first and the second element because the elements on these positions are true. Okay, I think you're ready for another exercise now. So get the second and the fourth number in my vector by providing a logical vector. Okay, we had my vector. And I can provide a logical vector just like this. So I want the second and the fourth. I don't want the first, I want the second, I don't want the third, and I want the fourth. You can notice here that instead of writing false, true, I just wrote FT, FT, which is interpreted as false and true because it's just a short version. And I will indeed get the second and the fourth element. So we can check this. Okay. Another way of doing this would be to create a logical vector which has these same values. So false, true. And then I can subset my vector by this logical vector, and I will get the same thing. Okay. Now I have few tricky questions. Why? Because R is tricky. No, it's not that tricky. It's just because if you understand what's happening here, you will understand you'll be sure that you understand subsetting as far as it's concerned now. Okay, so let's define some other vector like this. So some other vector is a numerical vector, and it contains numbers 1, 0, 1, 0, 1. My first vector, let me show both of them. My first vector is a vector that contains the words some words, p, awesome, and last one. So it's a character vector of length 4. What do you think will happen if we try to subset my first vector by some other vector? Okay, there are two possible outcomes for this. The first one is that this will be interpreted as true and false, and we will get the first, third, and the fifth position. And the second outcome is that, let's just try and see what happens. So is this. We get the first element 3 times. Why is that? Because when we subset from my first vector, positions which are saved in some other vector, we are subsetting it like this. So we are subsetting first the first position, which is some words, and then we are subsetting the 0th position, which doesn't exist, so nothing is returned. And then we are subsetting the first position again, which is again some words, and so on. So in the end, what we are subsetting is 3 times the first position of my first vector. This is why we get some words 3 times. If we want to convert this to logical vector, it can be done by using the function asLogical. And this will just convert all the ones into true and all the zeros into false. So when you try to use this vector to subset, what will happen? You are supposed to get now, because you're using a logical vector, you will get the elements in the positions which are true. So you will get the element in the first position, the third position, and the fifth position. There might be a problem because the fifth position of my first vector doesn't exist. So what will you get? You will get some words, awesome, and NA, which is not available, which is what is expected because it doesn't exist or is unpopulated. Okay, so if you understood this part, you are safe to continue because you can say that you understand subsetting by indices, by positions, and by logical inclusion. Okay. What can we do with vectors? Well, same as on numbers. You can do basic operations. You can add them together. I don't know how this is called when you subtract them. You can multiply them and divide them. So for example, if this is some other vector, which is just 1, 0, 1, 0, 1, and you multiply it by some constant. A constant in R, in this case, it means just one number. So it's a constant number. It has length 1, and some other vector has the length 5. If you multiply some other vector with a constant, all of the elements are multiplied by this constant, which is something that is expected, I think. Well, for me, it was expected. Okay. You can multiply two vectors of the same size without a problem. For example, if you have some other vector, which is 1, 0, 1, 0, 1, and you have a vector or a sequence of numbers from 1 to 5, if you multiply them together, what will you get? You will get pairwise multiplied vector. So here you can see that the first element in some other vector is multiplied by the first element in this second vector. The second element is multiplied by the second element, and you get 0. The third element is multiplied by the third element, and so on. So it's pairwise multiplied. Okay. The kind of awkward thing about R is that you can actually multiply elements, vectors, which are not of the same size. because why not? Okay, so what happens in this case? Let's say you have the first vector, which you already know what is, and you have another vector, which is just the numbers 0.3 and 0.1. When you multiply them together, this will happen. So first, you get a warning. Let me just do this. Okay, I'm just moving this into the new chunk so we can see this clearly. Okay, first you get a warning. The warning says that longer object length is not a multiple of shorter object length, which means that this object has the length 2 and this object has the length 5, and 5 is not a multiple of 2. Okay, but what do you get as a result? You get that 0.3 appears 3 times. Now, how is this possible? Maybe for some of you this is logical. For me, it was not on the first sight. But then somebody says, yes, but R does recycling. And I say, yes, but what does this mean? And he explains, well, if you don't have an object which is long enough, what R does is just copy pastes the numbers until it has enough. How is this logical? I don't understand. But it's really useful sometimes. You will see when. Okay, so what actually happens is this. Oh, well, this. R creates an object by multiplying, concatenating the shorter vector, just recycling it until it reaches the length that it's supposed to reach. And then when it reaches this length, it just does the normal multiplication pairwise. Okay, now in this case, you got a warning, which is fine. At least you know something might be off and this might not be what you're trying to do. But sometimes it doesn't produce a warning. For example, if you try to multiply, let's remove this. If you try to multiply sequence of numbers from 1 to 6 and sequence of numbers from 1 to 2, what you will get is just some numbers. Now let me explain what happened here. Okay, so as we know from seconds ago, if the two vectors are not of the same length in R, and if you try to do some mathematical operation on them, like multiplication or division or addition or subtraction, R will just recycle the shorter object. So this will happen. 1, 2 will become 1, 2, 1, 2, 1, 2. Okay, and after that, they will just be pairwise multiplied. Now, the problem with this is that this might not necessarily be what you are trying to achieve, and most of the time it's not. But R won't produce any kind of warning because it will only produce a warning when the second element, the vector length, is not a multiply. Well, sorry, other way around. When the longer element length is not a multiply of the shorter element length. So in this case, you're not even warned that something weird might be happening. So keep this in mind. Other than that, R is pretty nice most of the time. Okay. So what else can we do with vectors in R? We can do basic comparisons. So this is your some other vector. And if you try to see which positions are equal to 1, you have to use this equal sign. So what will happen? Again, the same as with multiplication with a constant, all of the elements in the vectors are going to be evaluated or compared with what you put there. So R asks, is the first element equal to 1? This is true. Is the second element equal to 1? No, it's not. Is the third? Yes. Fourth is no. And fifth one is yes. So what you will get a logical vector which will tell you which positions are true for the condition that you asked. So in this case, which positions are equal to 1? Okay. You can also ask for some vectors of the same size, are they equal? And in this case, of course, they will be pairwise compared. Since some other vector is 1, 0, 1, 0, 1, if you ask R, if where, in which positions is some other vector equal to the vector 1, 0, 1, 0, 1, it will give you true for all the positions because all of the pairwise positions are same in the two vectors. Okay.
I think we lost Maja. I think while we wait for Maja to reconnect, are there any questions? Does anyone have a question we can answer? Can be a pretty abstract one.
I was just wondering if any of you guys have used R, or nobody has ever done it, and you just want to, and what for?
I can see that Maja is back. Hi, Maja. I can't hear you though. If you're saying anything, I cannot hear you. But there was a question from Rihanna. I don't understand very well the last example. So I think Maja's lost again. So we can go through the last example then. Okay, let me open this. Hi, Maja.
Hi, can you hear me?
Oh, yes. Brilliant.
Okay. I can repeat the last example, no problem.
Great.
So it's this one with the basic comparisons, I guess. Okay. So if we want to check which positions in the vector are equal to some number, you can do this by using the equal sign. So when you do this, you basically ask R, tell me which position is the first position in your vector equal to 1. Is the second position in your vector equal to 1? Is the third position equal to 1, fourth, and fifth? And what you get, so this is the result, you get that the first position is equal to 1, the second one is not, third one is, fourth one isn't, and fifth one is. So you get true wherever the positions in the vector are equal to 1. You can also ask which positions in some other vector. Actually, you can also compare vectors pairwise. So if you have some other vector and you want to see if it's equal to this vector, it's supposed to be equal because some other vector is just a vector that holds these numbers. It's a variable, and this vector is temporary object that holds the same numbers. So if you try to see if they are equal, what will happen is R is going to compare them pairwise, and it will compare if the first element is the same as the first element in the second vector, the second one is the same, third, fourth, fifth, and the logic behind all this is that it will give you true for all the positions in the vector. And this is what happens. So for each position, you get that it's true because all of the pairwise comparisons are equal. Okay. So I hope this was better explained. So you get true, 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 because all the positions in both vectors are the same. All the elements in the same positions are the same. Okay. Thank you for your question, and please interrupt if you have any other questions. So, because if some of you didn't understand, it probably means that some other people don't understand as well. Okay. If you want to check which positions are greater than 0, you can check it by this greater than sign. Of course, you will get the first, the third, and the fifth position as true, and the rest will be false because the elements in the position 2 and 4 in some other vector are 0, and the rest are larger than 0. Okay, so the cool thing about what we learned now and previously is this. If you understand what happened here, you're ready to go to the next step. And if you don't understand, don't worry, because I will explain it and we will have some more examples there. So what happened here is this. We are subsetting some other vector by another vector, and this other vector is true, false, true, false, true. We said that when we are subsetting by a logical vector, what you will get is the elements on the positions which are true. So here we ask which positions in some other vector are greater than 0. Okay? And you see in the resulting vector that the positions 1, 3, and 5 are greater than 0. And then when you subset this vector by this logical vector, you will get the elements of some other vector. So your some other vector looks like this. You will get the elements which are on positions which are true. So you will get the first element, the third element, and the fifth element. Basically, you will get all the ones. Okay. If you had some other vector that looked like this, one, 3, 5, 5, 7, 9, for example, and you subsetted it by the same condition. So we want the SOV from SOV which is larger than 0. What will we get now? Since SOV is a vector that contains the numbers 1, 3, 5, 7, and 9, we ask when is it larger than 0? It's always larger than 0, so we will get true, 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 true. And we will subset this vector by a logical vector. So we will get all the elements which are on positions which are true. So we will get all the elements of this vector. This might not seem useful now, but it's actually really powerful because it's a fast way to subset a vector by logical expression. So if you want only the elements which are larger than 5, you can do it like this easily. So this will give you the pairwise comparison, which elements are larger than 5, and by subsetting, you can get only those elements very quickly. Okay. So it's important to remember that subsetting biological indices returns elements on positions which are true. Cool. I think now you're ready for your next exercise. The next exercise is this. Multiply your my vector by a vector that contains numbers 0.1 and 0.2. What do you expect to get? And check if what you get is what you expected to get by comparing it. Okay, so we have to insert a new chunk by Control Alt E. We check what is my vector because we don't remember anymore. My vector contains the numbers 15, 16, 17, 18, and 20. Okay, we have to multiply it by 0.1 and 0.2. Okay, I just copy paste this here. We get some kind of warning, but this is fine. What we're interested in is this. So what do I expect to get? Well, I expect to get this. I will save this in a vector named result, and I will show you the result. Okay, and now I want to check if I get what I expect to get. So is the result equal to the vector containing exactly what I copied now? Okay, so what will happen? Let me show you. So this is the result, and this is what we expect to get. By using this equal sign, R will compare them pairwise. So for each element, we will see if they are equal in both vectors. We expect to get true, 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 true. Now when you run it, you see that one of it is false. So how can this be? Okay, let's check again. Did we copy something wrong? Probably, but we didn't. In the result, 1.5 is equal to 1.5, which we expected. Okay, 3.2 is also true, but 1.7 from the result is different than 1.7 that we copied. Although it looks to us as if is the same number, this is a very big, well, it's not a problem. It's just a very big thing you have to have in mind when using either R or Python or any kind of programming language really, because it has to do with rounding of the numbers. So whenever you do multiplication or division by decimal point numbers, it's really not easy to save those numbers the proper way in the computer. So they're not saved so this number is not saved as 1.7. It's saved as something very, very, very close to 1.7, but not really 1.7. But the R doesn't want to disturb us, and it pretends like it's 1.7. Okay, so what's the problem with this? The problem is when you want to subset a vector to give you only those positions which are exactly equal to this, you will lose one number. So whenever you subset by equals, you have to be very, very careful that you didn't do any kind of division or any kind of multiplication before, because you will lose some results. When I first figured this that this happens, it was such a big problem that I actually went through all of my previous code and checked if I didn't do something like this before. Because it's really awkward that you expect to get some result and you don't get it just because it happens. And it doesn't happen with all the numbers, just some random ones. Okay. Now you have an exercise for you. So this is only a problem, I have to say, when you're checking with equal. If you're checking with smaller than or larger than, this is fine. Okay, the exercise for you is to return the elements in my vector that are smaller than 17. So how will we get this? We need to check which elements in my vector are smaller than 17, and we will do this easily by using the smaller than sign. And then when you subset by this, you will get the elements which are smaller than 17. Okay. Why? Again, like previously, because this will give you the logical vector, and it will, when you subset by logical vector, positions which are true will be returned. Okay. You can use logical operators in R. So logical operators are and, or, and not, and you can combine multiple conditions. This is something that we won't do because I think it's enough for you to understand how to subset by one condition. If you understand this, it's not a problem for you to subset by multiple conditions. Okay. Now there is one final exercise in this part, and this is to return all the elements which are divisible by 3. Okay, in the beginning, I mentioned how to catch something which is divisible by 3, or by any number actually, and this is to use the modulo operator. So if you want to see which elements are divisible by 3, they are those elements which will give you zeros. So when you do this, you will get true for all the elements which are divisible by 3. And when you subset by this, my vector from this will give you the elements which are divisible by 3. Of course, this works for any other number, because it works. And this is something that's extra. So return all the elements from your vector which are on even positions. There are at least two ways you can do it. There are many ways you can do it, but I will show you, well, 2. So you can do it by positions. You can say, okay, I know my vector has 5 numbers, so give me just the second and the fourth number, because these positions are even. This is not the smartest way, because if you had a large vector, then you will have to write a lot of numbers. You can say, give me the logical position. So don't give me the first one, give me the second one, don't give me the third one, give me the fourth one, and don't give me the fifth one. Which will give you the correct result, but it's also not the smartest way because, again, if you have a large vector, it will take you some time to type it. You can use recycling in your advantage in this case. Why? Because if you just write my vector of false true, it will actually return to you all the elements which are on even positions. How does this happen? Because R will recycle these elements until the length that it needs to get. It needs to get 5, so false true will actually be recycled into false true, false true, false, and my vector will be subsetted by this, which is exactly what we want to get. So sometimes, very, very, very rarely, recycling can be useful. Maybe some other times also, but this is the only case where it was really useful. Of course, there are other functions you can use on the vectors. I will just mention some of them. We won't go into them, but because I think it's, as you progress and learn R by yourself, it's not difficult to understand what functions do. The tricky part is, for me, was to get to this state of mind where you don't think in for loops as a programmer, but you rather think as, I don't know, subsetting. Everything is subsetting in R. Okay. So functions, different functions, for example, length, and then the number, the name of your vector will give you the number of elements in the vector. Unique will give you the unique elements in the vector. Table give you the unique elements and the number of those elements. So table of some other vector says that number 0 occurs 2 times and number 1 occurs 3 times. Then you can use sum, mean, standard deviation, or summary, which are just normal mathematical functions that you use every day. Very fast to use in R, but as I mentioned, so this is something that you will discover on your own when you will need it. So how can you get help in R? It's so you just write small question mark, and after the question mark, you write the name of the function. This will open here the help, but of course, this is not something that people usually read. What they usually do is go to examples and then try to copy paste those examples. R is smart this way, and it knows that, I mean, creators of most functions know that people usually don't really want to read a very big documentation. So there is a function called example. Example will actually run the examples for you. So you don't have to run them yourself, which makes it easier for you to understand what's happening and how some function is working. Okay. So with this, we are finished with the introduction to R. And if you push the knit button, what will happen is R will complain that it doesn't have some packages, of course, because this is a new surrounding for you. Okay, but after you install the packages, you will be able to get the document with all the solutions that we just wrote. So I don't think that this is going to take a long time. And yes, after it's done, you're going to see that all the solutions and all the code and all the text is now here, saved, and you can read it whenever you want. Or you can just do it again if you want. Okay, so with this, I finish my first part of the lecture. If there are questions, please ask now, because if not, we'll move to plots. Okay. If you're following, you can open the next. Yes, please don't be shy and ask questions. But if in any case you didn't catch something, in this next part, most of the things we just learned, I know it's a lot of things to process, so most of them won't be necessary for you to understand the next part. Okay, so the next part is ggplot. You can open the new document by going to these files and just clicking on the ggplot. It will write here that packages, data table, and ggplot2 are required but are not installed. So you can just push this install button. Why is this happening? Why is this happening? Okay. So if you do not have the files necessary, the files are available in the GitHub of NGSchool. And if you don't have the install button, you can install the packages yourself by using these commands, install packages. So you have to do this only once. Once you install a package, they will be installed for the rest, like until you update the R version. So you have to install them only once until you update R. But you have to say that you will be using them. You have to load them every time you want to use them. You load the package by using this command called library. So you can just push play, and this will load the packages data table and ggplot2. Here it says that data table is using 8 threads. It means that it's running on multiple, well, threads. We won't need multiple threads now, and especially if you're working on some kind of shared supercomputer or some space where you shared resources, it's good to understand that if you don't need some resources, it's better not to use them. So you can use the function set threads, set dt, the threads, set data table threads, and write the number of threads you want to use. So get dt threads is a function which will tell you how many threads you're using. I just use this not to use all the 8 threads that are available to us, but to use only one thread, because it's not necessary to use more. Okay? This part of the lecture, I will show you how to do cool graphs in R, which is something that will be useful to you, and I think it will be more fun and more dynamic lecture than the previous one. But for this, we need some data. So this function, if you press play, will automatically download from the location on my server the dataset that I prepared. The dataset looks like this. So it has 142 rows, and it has the observations. So it has 142 samples or people, and we noted their gender, their age, what continent they're from, and what's their height and what's their weight. The height and weight here, as well as everything else, is imaginary because I prepared this data by random sampling. So this is not real data. So just that you don't feel scared that somebody is 186 centimeters tall and 70 kilos heavy, or even worse, this. So basically what you need to see from this is that this data set has 5 variables. It has gender, age, continent, height, and weight, and it has 142 rows. This is a data frame, actually a data table, and this is the first time you encounter a data table. For what we will do now, the data table is not as different from vectors, not different enough for you not to understand it. I will show you where the differences are. But for now, it won't be a problem for you to follow. Okay, what I did, I just pushed the need button. So I get this pretty document because it's easier for me to explain to you the theoretical part, which I'm going to talk about. So in R, well, not just in R, in general, there are different variable types. We can see some, like there are categorical variables, which can be nominal or ordinal, and there are quantitative variables. They can be either discrete or continuous. When we say that something is quantitative variable, it just means that it's a number. When we say that it's discrete, it just means that it's part of a set of numbers. Let's call it like this. So it can have discrete values. It can have not predefined values, but the values are part of a set. Well, discrete. They're not continuous. They're not real. Okay, and when you talk about a continuous variable or continuous quantitative variable, you usually think about real numbers. So it can be anywhere in the scope, like anywhere on the line. Any point can be can be part of this variable. Okay. When we talk about categorical variables, we think about a variable that's like this. So it has multiple different levels. For example, gender is a categorical variable, and it can only like here the values of gender are only female or male. So they have different categories that they can take. And the continent is also a categorical variable. So the difference between nominal and ordinal variables, categorical variables, is that in nominal variables there are no like some level is not better than the other level. For example, we cannot say that females are better than males in this sense. Like we cannot say that Asia is better than Europe. Okay, this might be a bad example, but you understand. So, for example, if you have a categorical variable that's ordinal, an example of this would be months, because for each month, you know which one is before the other one. So is it lower or higher than another month? Okay. Why is this important? Because based on different categorical, I have a beautiful tip filler here. I'm sorry. So based on different variable types, you can plot different graphs. For example, if you have a categorical variable like this one, like continent, you can plot something that's called a bar plot. Bar plot just shows you how many samples or how many people belong to this continent. So in our data set, we have 80 people from Europe, we have 16 people from Asia, and we have around 50 people from North America. Okay? If you have quantitative variables and you have just one variable, what you can do with it, you can plot a density plot. Okay? The example for a quantitative variable is height. So here you have a density plot, which means so the higher the hill on the plot is, the higher the probability that the person who is male will have the height from 190 to 180 to 190. Okay, so basically it's a plot of, I wouldn't call it, yeah, it's a probability plot. You can look at it this way. So how do you interpret this plot? You see like where is the highest peak, and most of the people, well, actually the proportion of the people which correspond to the area below this curve will have this height. Here you can see obviously that people, well, it's a bimodal distribution for females, but males are generally larger or have bigger height than females. Okay. If you have two continuous variables, the example for this is weight and height. If you want to see if they are somehow correlated or somehow matched with each other, you can do a scatter plot. Scatter plot is just you plot one variable on one axis and another variable on other axis and plot their values as a point. So it's a two-dimensional representation. Okay? If one variable is discrete and the other is continuous, for example, here gender is discrete variable, it has two levels, either female or male, and height is continuous. So in this case, you might want to plot a box plot. Box plot, actually, in R, a box plot is not defined. So for a box plot, you always need to say what are the limits that you are plotting, because you can be plotting different things. You can change this what quantiles you want to plot and how far you want the hands to extend. So this is something that is customizable and always should be mentioned. If you don't want to plot a box plot, you can plot a violin plot. A violin plot you can imagine as just the density plot, but turned around. So it shows you some kind of distribution of heights for females and males. If you have two discrete variables, the only way like the way that you can plot them is to like plot how many of them there are and then just color it by the other discrete variables. So this is the, not the height, this is, okay, it's supposed to be the number of females, yeah, the count of females and males colored by the continent. So it's just the number of samples or number of people that we have in the data frame. Okay. Now we come to the cool part about R. So R is a statistical interface where you can visualize your data also. So in base R, plots look like this. So it's currently not important what this plot is, but what I wanted to show with this plot is that base R plots are not that pretty if you just use the defaults. So there's a package that's called ggplot that it's very widely used and that makes your default plots very pretty. So here I want you to understand that the difference between the default plot in ggplot and in base R is like very noticeable. For example, here you have small lines so you can see where the x-axis and y-axis are. You have a legend which tells you what the colors mean. The x's are named just by the variables and not by also the data frame. And it's just more in generally prettier. I'm going to teach you today how to make basic pretty plots by ggplot, and it's not that difficult, but it's so much easier if you never did any kind of plotting, because the logic behind ggplot was something that that took me a little bit of getting used to. So the logic behind ggplot is that you plot things by layers. So first you will define what your x and y variables are, x and y axes are, and then on this you will plot other things. I think it's best if now we went to the examples. So you can go to the ggplot markdown document and scroll all the way down to here, to the line 185. Okay, so we're starting with example, but this example is basically already an exercise because it will be easier to explain by doing. So first thing you need to do is to say, fill in the empty spaces so you get a layout. Layout means so you defined x and y axes in which we will use the dataset iris, and we want x-axis to represent species and y-axis to represent petal length. Okay, maybe before we use this, I want to show you what the dataset iris looks like. So dataset iris is a very popular dataset in R. It contains 150 observations. Each row contains the measurements for sepal length and width and length of the petals and width of the petals for some flowers. There are 3 flower species that were taken into account: Setosa species, versicolor species, and Virginica species. So for all of them, they have 50 different flowers. Okay. Now we want to see, okay, this. So the first thing you want to do if when you create a ggplot object is to define a layout, and as I mentioned, and I mentioned now again, so to define a layout, we first use the ggplot function we say which data frame we use, and we use this AES, which stands for aesthetics, to say which are going to be the x-axis and the y-axis. So here we just state the name of the variables from our data frame that are going to be x-axis and y-axis. And here we state the name of the data frame that we will use. Okay? So if we go back to the line 190, we want to use the dataset iris and x-axis to represent species and y to represent petal length. Okay, so to do this, we want iris, we want species to be x-axis, and we want petal length to be y-axis. Okay, this is the first step. When we execute this and show the graph, what does P look like? Well, P looks like nothing. Why is this? Because we didn't do anything with it. We just said what we wanted as x-axis and y-axis, and this is what we got. So now we see that there are 3 values for x-axis. There are setosa, versicolor, and virginica, and there is petal length, but there is nothing on the graph. So for R or for ggplot to understand what we want to do with it, we have to tell it. What do you want to do with it? We want to present a scatter plot for petal length for each group. How do we add the scatter plot to this plot? We just add geom point. So we have this P. P is this basic layout, and everything we do later will refer to this basic layout. So what happened here? Here, when you add plus geom point, R will make a scatter plot, having in mind that the x-axis is defined before, is species, and the y-axis is petal length. So for each observation, it will write one point, like wherever the petal length is. Okay, so in setosa species, some petal lengths are, all petal lengths are lower than 2. In versicolor species, petal lengths are between 3 and 5. And in virginica species, petal lengths are the highest. Okay, now let's color the points by petal length. How do we add color? We just, inside the geom point, add color is equal to petal length. Iris, petal length. Okay? If we run just this part, we see that the colors will change. Why? Because for each different, so each different color corresponds to different petal lengths. Okay. Now we also want a scatter plot, so we wanted a scatter plot, but this doesn't look so nice to us, and we changed our minds. Now we also want a box plot on top of this scatter plot. So the same way that we added a scatter plot on top of the empty layout. So you can imagine that you just have an empty layout, and on top of it, you just paste whatever you want to do with the data. So we pasted a scatter plot. Now we want to paste on top of all of this a box plot. So to do this, we can just add plus, and to add a box plot, you have to write plus geom box plot. Okay? This will actually create for you a box plot on top of the scatter plot. Okay. So I can mention this again. P variable contains, so it's an object that contains the basic layout. And this layout is valid for all the layers which we will put on top. So whatever is specified here in the AES, in the aesthetics, here will be the x-axis, and this will be the y-axis. And this will be valid, so whatever is specified in the aesthetics will be valid for all the top layers. If we want to change, for example, something, okay, we won't change it here, but if you want to change the aesthetics in just one layer, you can change it by using the AES, so aesthetics, in this layer. For example, okay. There's one thing that you can see here. So whatever we put in the aesthetics, here we put species and petal length. And these are just the columns of the iris data frame. Whatever you put inside the aesthetics, the ggplot will automatically search for this object as a column in this data frame. If you don't put aesthetics, for example, if you just put color is equal to petal length without the aesthetics, then ggplot will complain and say that this object is not found. If you put this into the AES, then ggplot will search for petal length within the iris object and it will not complain. So it will actually see that within the iris object, the petal length is a numeric vector and it's continuous, so it will try to color it differently. It will try to color it on a scale from wherever the values go. Okay, so whenever you use AES, whenever you use aesthetics, the ggplot will search for this object in the data frame that you gave it. Okay. This was the first example, which was the stupidest one. We can now take what we've seen and try to make a better example. Okay, if we want to see if there is a connection between the petal lengths and the sepal lengths in the iris dataset, we want to do a scatter plot where x-axis is going to be the petal length and y-axis is going to be the sepal length. First thing we need to do, as before, is set the aesthetics. So we say that we say to ggplot, okay, take the iris data frame and put petal length as x-axis and put sepal length as y-axis. We know that nothing will happen except the axis will now be defined. Okay. If we want to add points to the graph, we can use geom_point. So geom_point will actually add a scatter point. Scatter plot. Cool. What you see happened here is for each petal length and sepal length, we got 1 point. So it seems like there is some connection between the petal lengths and the sepal lengths in the flowers. Now we're interested, like, is this influenced by the species? So I want this graph to be colored by species. I can do this by using the aesthetics inside the geom_point just to change the color of the points. So you have to say color is equal to species. Now ggplot will color your points by species. What we see here is that the Setosa species has the lowest sepal lengths and petal lengths. The versicolor species has the sepal and petal lengths in the middle, and Virginica the highest. And it seems like the relationship, the correlation between petal length and sepal length are similar in Virginica and versicolor species, but is somehow different in the Setosa species. We can actually test this, I mean, we can actually plot the linear relationship between those variables by using a cool function called geomsmooth. So geomsmooth will try to fit the best line for all of your data. Okay, now what you have, let's say that you want a regression line. You can add method is equal to lm. And this will add a regression line instead of a curvy line. Okay. What you get here is the best linear approximation for the sepal length and petal length for all species. It's easy to do this for each species. You just have to say that you want to group, so that you want to do this separately for different groups. To say this, you can put inside geomsmooth because you want this method, this layer, to be applied only for different groups, so for each species. Inside, you can put that you want to change the aesthetics and you want to group your data by species. What happens now is that actually you get different regression models for each species. Okay. So this is a quick way to do this group-wise. Okay. There's also something cool. So this is now saved in the P4 variable. There's also a way to, like, if this graph looks messy to you, you can divide it by species. So if you want 3 graphs instead of 1, and you want each graph to have its own plot for each species, this is easily done by faceting. So you can add a layer, which is called facet grid, and just by writing species, the graph is now divided into 3 different graphs. You may notice here that the x-axis is the same for all 3 graphs, and also the y-axis is the same for all 3 graphs. This is something that ggplot does intentionally, so it's easier to compare values between groups. A different way that you can facet is to use facet wrap. By using facet wrap, like in this case, it's very similar. Sorry. Dobro. So it's similar in this case, but the difference between facet wrap and facet grid is that by facet grid, you actually create a grid of plots, for example. In the first part, you say what you want in rows, and in the second part, you say what you want in columns. So while this gave you the grid by columns, because we put it in the second part, if you want the graphs to be aligned vertically in 1 column, but in 3 rows, you can use this. So ggplot is very versatile, but what I want you to understand from this lecture until now is that the basic logic behind ggplot is that you once define your x-axis and y-axis, and this is the basic layout that you define, and everything that you add later has the same values of x-axis and y-axis, so it has the same aesthetics. You just
you will start with us.
Yeah, with the animals.
Yes. Didak and Maria.
Nice to meet you.
I mean,
so you get it. it has the same values for x and y axis. The only thing that changes is that you put the layers on top of the
Ana María es italiana.
on top of the
También un poco de...
primary layer. So you put layers on top.
Ah, perfecto. Bien.
Okay.
I was that so in all the stuff. And now is that?
I have for you two exercises
I'm sorry for I didn't know that you were in
that you can do by yourself. And the exercises are to recreate the plots. This plot is easy to recreate, and I think it's going to be fun for you to go through these examples that I've showed you by yourself and try to recreate this plot alone. And then there is this other plot, which is a bit more difficult to reproduce. But I think that with the hints that I've given you, it won't be a problem. And you also have the solutions for both of these plots in this ggplot solved markdown. Okay. So with this, I will conclude the ggplot part of the lecture. We can save this and we can knit it into a pretty document that you can later use for your presentations or for whatever you need. And we will, after this, we can go through the third part of the lecture. And this third part of the lecture is using these two data frames that we used now. So the iris data frame and the data frame with heights and weights of people, and trying to do some analysis on them very efficiently with data table. Okay. So to do this, we will just open the data table markdown document and read in the data table again. So I will do some examples on this data table, and you will try to repeat it or repeat the same by exercising on the iris data table. So you have the package installed, and you don't have to install it again, but you have to load it in case you didn't load it before. If you already have a data frame, you can convert it to data table by using this as data table. But in our case, this is also not necessary, because actually DDF and this are the same object. So this was already a data table. So as you can see, the data table and data frame are basically the same thing. It's just a table that you read from somewhere that you have. Like, you can imagine it being an Excel table, and you read it into R and you analyze it more efficiently here. Why I like this package so much? Because all you need to know is how to subset a vector. Once you know how to subset a vector, it's quite easy to do very complex operations by very efficiently. Okay, so the first thing that you will learn is how to select rows. So if your data table looks like this, and you want to select rows which are, so you want to see how many people are taller than 180 centimeters, you will select the rows the similar way that you would select a vector. So you ask, where is the height higher than 180? And for this, with this, you can subset your data table, and you get only 51 row. And in this 51 row, the height is over 180 centimeters. So if you understood how to subset a vector, it will be no problem for you to subset a data table, because it's basically the same thing. If you want to see how many people there are without checking the number, you can use the function nrow, which will give you the number of rows where the height is higher than 180, and it will of course give you 51. Okay, so we've seen that selecting rows in a data table is absolutely the same as selecting elements in the vector. So instead of using, you always use some kind of logical index, logical expression, and subset the data table based on this logical expression. Whatever you put here, all the rows, and so in a vector it was all the elements which were true. Now all the rows for which this expression is true will be returned. Okay. In data table, so they are data tables are different from vectors because they obviously have rows and columns. So you can both subset rows and columns. This is easy to do. If you give just one logical expression or one coordinate, it will subset rows automatically. But if you give two coordinates, it will subset rows by what's in first coordinate, and it will subset the columns by what's in the second part. So what's in the second coordinate. If you want to select the age and the continent of the first 5 people in the table, so if your table looks like this, to select first 5 people or first 5 rows, you just write 1 to 5. And to select only their ages and continents, you have to put a dot. So in when you select it from a vector, you needed to put a C. Okay, here you don't put a C, but you put a dot. The only difference between these two things is that dot is short for list, and actually data tables are implemented as lists. This is nothing for you to worry about because the difference between vectors and the data table is not really that high, because just instead of using C, you have to use a dot. And then you just use the names of the columns that you want. So this will give you the first 5 rows and the age and the continent from this data frame, data table. Okay, first 5 rows and only the age and the continent. So first 5 rows, only the age and the continent. Okay. If you want to use column names, this is how you do it, but it's not something you will probably use that often. Okay. You can also select everything from age to continent. For example, we've seen that in a data table, let's say that we want all the columns from age to height, for example. We can put here this, and this will select first 3 rows and all the columns from age to height. So this will work. Also, if you want all the columns except for age and continent, you can use a minus sign. Okay. Also, if you want to exclude something, you can use a exclamation mark, so a not, which will give you everything except for the age and gender. Okay. The first exercise for you is to convert iris into a data table and select all rows in which the sepal length is smaller than 6.7. So we will call it iris dt. And to make a data table, you just have to write as data table. How do we select all rows where sepal length is smaller than 6.7, we just write that we want to subset by one coordinate, because subsetting by one coordinate will give us all the rows. And we want to subset by this condition, sepal length is smaller than 6.7. So this will give us all the rows in which the sepal length is smaller than 6.7. If we want to show only columns sepal length and species, we could do it like this. So just in the second coordinate, we put a dot and write the names of the columns that we want to use. Okay. Now, the really cool thing about data table, and this is the thing where I will finish my lecture, because everything else will be maybe too advanced for this lecture. The really cool thing about data table is that in the second coordinate, you don't necessarily only return the column, but you can make some operations on the column that you return. For example, if you want to calculate the mean height for all the people, so you have your data frame and you want to calculate the mean height, so this will return to you just the column height. But if you want to calculate the mean of this, you can just write mean of height, and it will automatically calculate the mean value for height for everything that you selected. So, as before, for example, if you select only the females, ddf dt, so you only want gender is equal to female, and you want only the mean heights, what will happen here is that first your data table will be shortened. So it will be filtered in a way that only the females remain. And then, so this happens first, and next, the mean of the variable height will be returned. So the mean height for females is 171. Similarly, the mean height for males can be calculated, of course. Mean height for men is 176. Now, another really cool thing about data table is that you don't need to filter yourself and calculate the means or whatever you want to do with the columns. You can say that you want to do this operation for each group. So we know that gender here can only be male and female. If we say this, ddf dt, so if we select all the columns, we don't filter anything, so there is nothing in the first coordinate, and we say that we want mean height, we can do it by group. If we use the third coordinate, and if we write gender in the third coordinate, what will happen is we will get the calculated mean height for females and males separately. What happens here is that data table actually creates separate data tables based on all the different levels that you have. So it will create a separate data table for females and separate data table for males. And then it will calculate whatever you said. So in this case, it will calculate mean height for females and mean height for males, and report this back to you. So by using data table, you can be really efficient. And this is really just the top of the iceberg from what data table does. But I don't want to overwhelm you with everything. Realistically, you've just heard half of all my lectures, I think. Well, 2/7 of all my lectures. And I hold a really, really intensive course, which is usually 7 weeks long. And you've just passed through 2.5 weeks in 2 hours. So not to go any further, I really recommend you to take the time yourself and understand just how to subset a vector and then how to subset a data frame. And then when you know this, to go through this by yourself, so through this entire notebook. And I think that by understanding how data table works and how powerful it is, and by knowing how to plot all these things, you can be a very successful data scientist very easily. So it would take you around few weeks to come from basically 0 to hero. And this is how you should learn R. Please don't ever use for loops in R. With this, I will finish. Please, if you have any questions, ask them. If this was too much, I really apologize.
Thank you, Maja, for an excellent workshop. Guys, do you have any questions?
Yes, I think it was a bit overwhelming. I'm sure it was.
Yes, it's a lot of material for the first time, for first contact with R. Thank you very much, Maja. It was really nice. I think many people will join it on YouTube after the workshop.
Thank you very much for inviting me.
Yes, and thank you everyone for participation and question during workshop. Next week we will have the next workshop, the second part of Introduction to Python. It will be conducted by Kasia. Also, please don't forget to fill out the feedback form. In a while, we will share the feedback form link. And thank you very much, and see you next week. If you have some questions, it's some short time to ask.
I'm also pretty sure that if you have any questions and if you're going to do the materials that Maja have presented, you can ask your questions on Discord. We'll be here, we'll be checking, and don't worry. You can always ask.
Okay,
Yes,
guys,
so,
thank you for listening, and I hope it wasn't too much, but I hope it will be useful. So see you next week.
Yes, see you. Thank you.